Right, good evening everyone and welcome back to Teaching Physics. What we're going to do is this topic all about the thermal side and energy ideas of thermodynamics, which is actually what we've already studied when we're talking about energy. All of this links together because when we talked about energy before, it was all about internal energy, and this is really getting inside materials. So going to start off by looking at the ideas, the general opening of the idea, and then it brings all these other things, some of which you've done before, specific heat capacity and so on, and then linking in all the ideas about how and why that happens. So we're going to bring in kinetic theory later. The first part is actually all about energy of materials, and when we look at the gas laws are actually about a quantity of gas, for example, not what's causing them to happen. Okay, so kinetic theory is very definitely a separate part. It's the mathematical bit that's very much about statistical modelling. The first bit is actually just looking at kind of experimental data, and this is one of the big experimental sections. So you've already got a bit of background to say. We're going to cover quite a lot of different things, and as part of this there is a derivation that you need to know your way through. It's quite a long derivation, but again it's knowing the ideas. Okay, and all of this in the end, 200 years after this whole story started, probably a bit more actually, we brought in the idea of particles to explain it. Boltzmann bringing those together. So it all links through those particle models, the kinetic model as it's called, kinetic theory. But yeah, we're going to look at the macroscopic and then go smaller and smaller. So revision wise, you can link it all back to the particles. But let us start with the general idea. Okay, now I've got the basics, which is around what you've got in the videos that I've shared you a link with. So talking through a three-dimensional model, but for the purposes of tonight, I'm just going to do you a little quick model. Okay, so we're going to start off with the idea, and this doesn't matter what the particles are in, but if you've got yourself a whole series of particles in some sort of pattern, it doesn't matter how, you know from key stage 3 that those seem to indicate a solid, but they could actually be a gas that just happens to all line up. The thing that makes it solid is that all of them are held in a rigid structure. So when we're talking about most materials, solids and liquids, you've got this bonding effect. Now some of them are solid bonds, which make it solid, fixed bonds, but others might allow them to move past, but they're all really, of course, about attraction. So it doesn't matter what the bonds are, you've got a force of attraction that holds these together, and that force means that if we try and move them apart, we have to push at a rate that's push more than this force, in which case we have to do work against this. So this is what leads us into this idea of talking about energy in bonds. Okay, it's the energy stored up very much like a spring. It works in a very, very similar way. Even before we knew about particles, a certain Mr. Hooke, Robert Hooke, had actually proposed this theory on the structure of matter, and actually is a very good theory. So it very much acts like springs. You pull them apart, and until you get to the point where they break, the forces get bigger and bigger and bigger, so it's harder to separate them. So that's the basis of everything. As again you learn to key stage 3, if we manage to break them and we start breaking down these bonds, so we've put enough energy in to make these move enough, it's actually all down to that kinetic energy, so these will vibrate more and more. If they vibrate enough, the forces moving them apart are enough to actually break this bond here. They become free, it becomes liquids, they are loosely attracted to each other as they get close together. But yeah, it's that main idea that, if they are held rigidly in place by very strong bonds, it's a solid. Without those bonds, so just mere attraction, you've got less forces holding them, you've got less potential energy, And of course, if you manage to break them all apart by separating them far enough, then you have a gas, and these are by this time free to move around, and they have so much energy that they're moving really fast. So they're not just vibrating, they have translational energy. They're shooting along. Okay, so it's not really different things, but we need to consider both types of energy. So if we're looking at descriptions, again, basic ideas, just in a nice, clear, short way. It's all about the particles we know now, but basically these ones are particles vibrating, and it doesn't matter how cold it is in real life, they're always going to be vibrating, and it's in a fixed structure, in a dense fixed structure, really. So that is what means, that's what causes our solids to not change shape, for example. Anything where the structure can change is, by definition, not solid. It's going to be a liquid. So things that are a bit awkward, toothpaste, it's a liquid. Okay, it might be quite solid in what you think, but its particles aren't fixed. They can move around. You can change the shape of it. So again, it's a liquid. Other materials like glass are liquids because eventually they will run downhill very, very slowly, but they do. So what we're going to talk about here is internal energy. So I'm going to bring in a thing that's not particularly in the course, but you'll see it around in a lot of books. So the internal energy summed up as U, no idea why U, but just keep it simple, is, and the key thing, both. Kinetic energy, I'll just put kinen, of particles, and, crucial bit, it's that potential energy, it's that stored energy within the bonds. I'll put it on its other way around, energy stored in bonds. So when we talked about that new way of looking at energy last year, it was talking about stores of energy. We're talking about internal energy, energy within substances, pretty much all the time. So this really is what we mean by it. So again, Devolves bonds for the chemists, ionic, covalent, metallic, it doesn't matter what it is. When we get to liquids, the particles are what? Are they moving around? Well, they're actually mainly still vibrating. Okay, but with more energy. Okay, and the key point is that they're in close proximity to each other, and because of that, closeness, you have those forces there. So the bond, let's say the bond forces are reduced. So what that means is, so there is less stored energy. Okay, I just realised I missed out a letter there. Stored energy. Okay, so the potential energy is reduced. Potential energy is less. Kinetic energy is more. They don't add up to what we had before. Okay, so there's less stored energy, but much more kinetic energy. The loss in potential is much smaller than the gain in kinetic energy. Okay, what that means is temperature, which we'll go into in a second, which basically tells us about the energy of each of the particles, okay, of each one. The temperature is hotter in a liquid than when it's that same material's in its solid state. Okay, ice, water, for example. So there's got to be more energy in it. So although the potential energy's got less, the kinetic energy has increased and a bit more. And then we get to the last stage. We basically, as we know from gases and plasmas going on, so ionically charged, so hot they've actually lost their electrons, for example. They've emitted all their electrons. These are moving freely as you're well aware, at high speeds, at high velocities. Okay, the only forces are basically, for what we're going to consider, are only during collisions. Okay, very, very important idea for our derivation later. But yeah, there is no potential energy at all. Okay, so zero stored energy. Okay, put that in brackets. So, in other words, at this stage, U is just kinetic energy. Okay, doesn't mean they're moving in straight lines totally. Some of it's spinning, some of it's vibrating, and so on. So there's different types in which it can move, but it's all about movement energy, all about kinetic energy. So the whole thing of that is we're changing how the energy is stored, how it exists within the structure. So we call it internal energy, but as it says up there, it's basically the sum of the two types. And from the videos that I've shared with you, you can see that actually it's quite random. Okay, so they're not all the same, you know, they don't all move in the same way, but that general idea of losing potential energy but gaining much more kinetic energy kind of runs through. And then the key point with it all, hence this arrow down the side, is the total energy is going in that direction. So as you go down, the energy within the substance from solid to liquid to gas is increasing. It's getting more and more energy, and we recognise that, we detect that as getting hotter and hotter. Okay, so let me just move that. Now, just to bring it all in, and we need to be really careful with language because we can be wrong. Particles are moving around, they have kinetic energy, but if we look at distributions, it doesn't, this whole Boltzmann distribution as it's known, doesn't matter what the temperature is, we still get this kind of peak. We will have the average, okay, and we're going to just call it average at the moment. We need to be very specific with it, but we'll do the maths when we get there. The average value is increasing with temperature, so at 300 degrees it's here, 200 degrees the average is there, 100 it's down here. So we're going up and up and up, but we have this big range on all of them. Okay, this top end will be around about 15 to 30 times bigger than the average. So actually this isn't a great diagram, it skews more and more across here. Okay, so some particles will be going way faster than the average, and of course some will be going way slower. Okay, so we get this range. So the easy way of describing it is when we're talking about the average kinetic energies of all of the molecules. Okay, now I've used particles up here because actually that's kind of more correct, but the exam boards will want you to talk about the molecules in the substance, and that's because of that whole idea of moving with a higher range of speed. Okay, so ranges we'll cover with the mathematics. There's different ways of doing it. We're not going to use the mean, so we're going to keep away from that, but we're going to link everything into this. Now, at a macroscopic scale, on a large scale, this whole idea of internal energy, we didn't know about particles. Literally 1905 was the evidence that convinced people that everything was made of particles, Einstein's first paper. We've known around about it for thousands of years. Democritus, Greek philosopher, came up with it originally, but we don't need this. We don't need these explanations. All the theories came first. So we're going to work away from that and we'll pick up with general things. So when we're talking about internal energy, we tend to actually talk about specific heat capacity. That's what is going on when we talk about internal energy. It's actually how much energy to heat and cool and change. Okay, so that's our idea of stored energy. So we'll stick with that big idea stuff. But key things that you must be clear in is linking in with those energies. So Thermodynamics, okay, is the flow of energy. This is a really, really important statement in here. It's the main idea. So when we talk about thermodynamics, we don't necessarily mean heat. It tended to be heat because in the old days it was all discovered through steam engines and so on. But we're talking about those energy stores that you have been doing since year 6 probably, and the energy flowing between them by work or by photons. That's thermodynamics. It's that movement of energy or transfer of energy. So for us, what we're going to look at in this chapter is mainly about that vibration, and so it's all about making that vibration spread out. For those that have done a bit on empathy, it's all about increasing the empathy of the universe. We'll come back to it later in the chapter. So yeah, it's all about things that have more energy, high temperatures, to low energy, low temperatures. Okay, so it's ripples spreading out on a pond is thermodynamics, because the bit in the middle has big vibrations, and then they're going to spread out smaller and smaller until they're as evenly spread as possible. That is this idea of thermodynamics. And if you watch certain programs, things like the heat death of the universe and stuff, it all links in with this thermodynamics. All comes back to this. So key point is this idea of heat flowing, heat transfer, needs something to drive it, and that driving thing is the amount of energy of all of the particles. So it's the temperature, which is the average of the particles. It's that temperature that causes heat to spread out, the energy to be transferred, if the surroundings are at a different temperature. As I say, going from hot to cold. If they're in thermal equilibrium, then no net heat flows. Particles may pass their energy outwards, but the energy in the particles outside will come in just as quickly. Okay, so it doesn't mean they're staying the same. Energy's transferred, but there's no net. It adds up to 0. Okay, so it does lead to confusion, and you get these kind of ideas where you listen to people, for example, how do you keep ice cold? Well, wrap it in a blanket, wrap it in a fleece. But that's what you keep hot things in and keeps them hot. Well, that's because it's reducing the flow of heat. So it doesn't matter if the heat's going in, trying to melt it, or the heat is in this hot object trying to get out. If you wrap it in some sort of insulator, then it will keep it hot or it will keep it cold. Okay, so it's all about heat going from the hottest area to the coldest. Now, just to bring the context together and bring those two together, we need to talk about temperature in a little bit of depth. And unfortunately, it means we need to talk about scales. And scales are very interesting because we need to actually have some sort of measurement. And this is the thing that makes it flow. So energy flow requires a temperature gradient, difference in gradients, compared to difference in thickness. So if you have thick insulation, the gradient is less, the flow rate is less. But what do you measure the theta in? Okay, and that's where our temperature scale comes in. And we're going to use 2 different symbols. So you may have used theta when measuring specific heat capacity. For that to be really correct, you should be using the Celsius scale. Originally called the centigrade because it gave 100 gaps between pure ice and water. But now we have many more fixed temp points that we can measure things at, not just pure water boiling and pure water freezing. Because we've got more fixed points going much higher temperature and much lower, we've changed the name to Celsius scale. So Celsius scale gives us that, and it's from that we discovered this thing called absolute zero. Now, absolute zero links back to here, is where particles on average in a substance have no energy, so 0 energy. And if at that point, you'll find that as we go back to look at this graph a second, as we go down in temperature, the range of speeds gets smaller and smaller and smaller. At 0, absolute 0, none of them are moving because the peak is so narrow that all of them have the same energy which is 0. They're not moving at all. So if you imagine gas particles and they suddenly stop moving and fall down to the ground, you've got absolute 0, or thing causing it will be absolute 0. So, which leads us into a better scale. So we'll move away from Celsius, we'll move into the Kelvin scale. Now, just be careful, these are known as degrees Celsius because it's a range, it's a comparison of temperature. Okay, so 100 degrees means 100 degrees higher than the other one. What we've got here is an absolute scale based on 0 energy. So we take the 0 temperature at 0 energy. Now I'm going to get you to do an experiment on this, but it was William Thompson who, as part of his role for science advisor, basically science researcher in Scotland, was known as Lord Kelvin, or he got that title. So it comes from that we get the Kelvin scale. But basically, a lot of readings. By taking those really, really carefully, these are very rough, but take them very, very carefully. If we keep going down in temperature, you'll find that the pressure of a gas gets smaller and smaller and smaller until almost, not quite straight, it hits at a certain point. If you do it with another volume or another substance, okay, even if we only go down to 0 degrees, they'll all extrapolate backwards, they'll all link backwards to the same temperature. And that same temperature is, on the degrees Celsius scale, minus 273.15. For the exams, minus 273 will do. Now, the scale's the same, the change is the same. We go up 12 Kelvin, we go up 12 Celsius. It's just the 0 is in a different place. So there's our 0 degrees Celsius, but it's kind of meaningless because you can go below 0. Okay? Whereas with Kelvin, we can't go below 0. 0 is the lowest it can be. So some basic questions are that whole idea of trying to get the absolute temperature. All our calculations are going to be based on this absolute temperature. So you need to be able to calculate that absolute temperature from degrees Celsius. Okay, so nice and straightforward. All we need is, I'm going to call it theta. I'll put a C for Celsius. Is going to equal the temperature in Kelvin. So capital T. Don't get confused with time period. You'll know the question is about heat. But you take that off and you subtract 273. Okay, so if that was 273 minus 273 would equal 0. 0 degrees C is at 273 Kelvin. You're just sliding that scale along, so that axis comes back to here. So that's all it is, you're just subtracting it. Okay, and as I say, don't worry about the 0.15. Now, how does that all link together? Well, the important bit is, and this is where internal energy comes in, the whole lot links, all those ideas of stores and energy transfer, links through this work done by Joule and Watt, both of the Jameses, and Isambard Kingdom Brunel, and Stephenson with his rocket, his steam engine, and all this, all that research. Joule and Watt are the people who did the work, hence the science aspect of it, which hence the units, joules for energy, watts for power. But it links together with these fundamental laws, and these are really, really, really important about the whole of the universe. It all depends on, we can't escape from these laws of thermodynamics. Now, unfortunately, they realised they needed one after they deduced the other laws, so they went backwards and produced the 0th law afterwards. Okay? And what that's saying is that if two objects are together and they are in thermal equilibrium, no heat is transferring, they must be at the same temperature. If the second object is at the same temperature as the third object, then the first and the third object must also be at the same temperature. Yeah? So if we wanted to know the temperature of a substance, and we have that substance in hot water, well, we can put the thermometer in the water even though we're trying to find the temperature of the substance. We know that they must all be at the same temperature if the temperature is not changing. They're all in thermal equilibrium. So, a little bit of kind of very important fact. If that wasn't true, none of the others would be. However, if we do the other one, let's go for this idea. So, the total energy, basically, we can simplify this. We're not going to do the full versions, but the total energy in a closed system. Okay, now that's very important when we get to the gas laws. That means the energy can't escape. It's all there somewhere. Yeah. So it's, for example, if we were talking about particles in this case a piston, but if we had it in a balloon and we did the calculations for gases, it all works fine. But if there's a leak in the balloon, it's not going to work fine. Okay, so that's not closed. So one that is sealed, that is a closed system. The Earth is a closed system. Energy is kind of contained within. So, basically, total energy in a closed system is conserved. You know that more generally as conservation of energy law. Okay, but what that summed up as mathematically is if you had a change in Q, and this can be written in different ways, it all depends if you're saying in or out, but basically this equation is the first law of thermodynamics. This is all about heat. Okay, so Q is often used in equations for heat rather than E for energy, so these are all energies. This is your internal energy, and this is work done. So, what we can do, we can, without changing the particles really inside a substance, the internal energy. Okay, so this is our delta U in here. Okay, and the delta means change, but we'll come back to it. So here's our internal energy. If we change that internal energy by doing work, well, we can make the gas change its behaviour, or we can make it go hotter. Thinking about a pump, a bike pump, if you pump that by doing work, if you squash the gas, it doesn't have to get warm. Yeah, so you're actually increasing the heat. So energy in, energy out, or energy in, energy out. Okay, so for this example here, I'm going to say energy in. Okay, sometimes say you can have delta Q plus delta U equals delta W. You don't need to think about the minus. The minus depends on if it's going in or out. So these ones are going to be internal energy of the substance. It can't go in or out, but how it changes. And work done is going to be out. Okay, so that'd be like the opposite of that. So if I was adding it up, I could have 0 equals that plus that plus that. One of them would have to be negative because it's coming out of the system while the others are going in. Okay, so example here. If I take some heat and I stick it in to a piston, I take piston in your car, yeah? We squash it, it makes it more active, it gives the energy to the particles inside. We then ignite it with a spark and the piston gets pushed out. You have work being done. Okay, so physical change in size, work done. Changing it by heating it up or cooling it down, that's the Q. And the effect is what happens to the particles inside, and that's your internal gas, internal energy. Okay, now just put a little star by this. In chemistry, okay, this is what you mean by enthalpy. Okay, so when you're talking about enthalpy, it's still all about the conservation of energy, but it's that work, it's what it can do. So, second law, is that this, don't get confused here, this is not enthalpy, this is entropy. Okay, and we'll go over a little thing underneath. But the rule is the entropy of the universe increases over time. Massively important. Okay, this means nothing is 100% perfect. So we're saying here in a closed system everything is perfect, but actually over time it gets less and less perfect. Energy is always conserved, but what happens is this entropy, this randomness, okay, so randomness of the system, when we say system, whatever it may be, oops, can't spell, it could be the universe itself. So the thing that has the energy in, this randomness of the particles, for example, gets more and more over time. What that says is energy spreads out. Okay, you drop things on the floor, they smash and go into smaller and smaller bits. Rocks over time break down into smaller and smaller pieces. All of that is the second law of dynamics. Your hot drink will cool down and down and down. It'll still be warm, still have internal energy when it's at room temperature, but you can't do anything with it. You can't warm anything up with it. So what basically, in terms of a lot we do, is this means there is, I'm going to put in brackets here, less basically energy is available to do work. So over time, all your energy just gets spread out more and more and more, gets thinner, and it becomes less and less useful. You can't do anything with it. Okay, so energy is conserved, but energy spreads out. It's not 100% efficient, nothing is, otherwise you'd be breaking that second law. And then the third bit, basically, as this idea of temperature increasing, so as I've written something weird in my notes, as the temperature approaches zero, then the entropy approaches zero. Because if we think about what that means, the randomness, as temperature approaches zero, entropy goes to zero. Okay. If our particles are bouncing around in a gas and they lose their energy, where they're going to end up with, they're rolling around on the bottom until they have no energy, no temperature, then they stop. And they're not disordered, they're just sat there and they can't go any more random. Okay, they are at the lowest possible energy level, and that is when we have zero temperature, which basically is saying this absolute zero, everything stops. Okay, so energy is conserved, energy spreads out, not 100% efficient, and basically everything's based on that 0 point temperature. Okay, so those are the laws of thermodynamics. I'm going to break into a second part because we'll look at what that means, but that's really kind of a quick revision, so we'll leave that to a second video. Okay, cheers guys, good night.